Welcome to the proof of convergence of Jacobi's algorithm. Now, Jacobi's algorithm, as we have seen it, is somewhat strange. It is like solving a Rubik's cube, cube by cube, but without taking care of the cubes that you have already solved. Now, if I tell you how to take a particular cube to its correct position, and then I tell you how to take another cube to its correct position, and you do both these steps one after another, there is no guarantee that both the cubes will be in their right destination. Because when you solve for the second cube, it is quite natural that the first cube will get dislocated from its true position. Now that is precisely the situation with Jacobi's algorithm. We are trying to kill all the off-diagonal entries one by one. So we first kill one off-diagonal entry and then we try to kill another off-diagonal entry. Now, what is the guarantee that this does not cause the first off-diagonal entry to pop up back again? Is there any such guarantee? Let's see. So here we have one example of a symmetric matrix. Here I can see that the largest absolute of diagonal entry is that minus 29. So in the first step, what we shall do is we shall try to kill that one. So we do one step of Jacobi, the same Jacobi algorithm that we used in the last video. So we have this. So you see that quantity that is supposed to be 0, but it is pretty close to 0. It is 10 to the power minus something very large number. So it is essentially 0. So we have zapped that particular off-diagonal entry pretty successfully. Now suppose I carry out the same thing once again. And this causes that old entry to become non-zero again. So you see, there is really no guarantee that terms that you have, that is entries that you have zapped once, will not pop up back again. And that is what makes the proof of Jacobi's convergence result slightly tricky. So we see that there is no guarantee that the individual off-diagonal entries are going monotonically down to 0. They will keep on bobbing up and down. However, what we can show, and that is interesting, is that the total sum of squares of all the off-diagonal entries, that must go monotonically down to 0. So first let's give it a name. I shall call for a matrix A, a symmetric matrix A, f of A, I am defining a function, f of A, that is equal to the sum of squares of all the off-diagonal entries. I will show that as you plug in different matrices in the sequence that you generate, A, A1, A2, A3, etc., f of An will converge to 0. That will of course show that each of the individual off-diagonal entries must also go to 0 because we are working with real numbers. So if the sum of square goes to 0, each of the individual numbers must also go to 0. We make a simple observation. We are always pre-multiplying and post-multiplying our matrix by orthogonal matrices, those Given transformations, those Given rotations. Now if I multiply a vector by an orthogonal matrix, we know that its norm cannot change. If you merely rotate a vector, you cannot change the length of the vector by just a rotation. So the sum of squares of each of the columns will remain the same after you pre-multiply the matrix by that Given's rotation from the left. Now if the sum of squares of all the columns remain the same, then the sum of squares of all the entries in the matrix must also remain fixed. The same thing, of course, holds for the post-multiplication part. When you are post-multiplying, multiplying from the right by another given rotation, the transpose, the same thing works for the rows. Here, each row will retain its norm square. That is, the sum of squares of all elements in any given row must remain constant. And again, if the sum of square of all elements in each row remains constant, then the sum of squares of all elements in the entire matrix must remain constant as well. And this gives us a very important observation. Each step of the Jacobi algorithm will always keep invariant the total sum of squares of all the entries in the matrix. Since the total sum of squares of all the entries in the matrix remains the same after each Jacobi step, we must be moving around the sum of squares from one entry to another. Because the total is always the same, we are merely redistributing those pieces of masses, we might say. Now we are trying to show that the sum of squares of all the off-diagonal entries will go to 0, which basically means as you are redistributing these masses, more and more mass is being accumulated along the diagonal, and the off-diagonals are getting depleted and the diagonal is slowly going up. So that is what we are going to show. So we shall try to do certain technical inequalities to figure out exactly how the off-diagonal sum of squares are going down. So we are trying to show that this quantity Fa, which is sum of squares of all off-diagonal entries of the symmetric matrix A, will go to 0. So if we start with our original matrix, suppose I call it A0, then we compute A1 by doing one Jacobi step, then I compute A2 and so on. I want to show that f of an will go to 0, and that will show that each of the off-diagonals must also go to 0. Now let us start a few notations. Suppose this is my matrix A, n by n. So these are the n diagonal entries. In each of these halves we have some entries. Suppose I have capital N many entries in this half, the equal number of entries in that half. So n is actually n into n minus 1 by 2. So if you want, you can have this formula n into n minus 1 by 2. Now at each step, what we are doing is we are picking up that of diagonal entry which has the maximum absolute value. Suppose I call it P. So P is the entry, an off diagonal entry with the maximum absolute value. So P is that off diagonal entry with maximum absolute value. Since it has the maximum absolute value, so we can immediately say that f of a must be less than or equal to twice n p squared. And why is that? Because if I square all the off-diagonal entries, each of them must be less than or equal to p squared, and there are n of them, n on this half, n on that half, so the total can never exceed 2n p squared. So I already have one inequality. Now let us see what happens when I do one step of the Jacobi algorithm. Suppose that we are considering one single Jacobi step. We are at ak and we are moving after a single Jacobi step to ak plus 1. Now how do you carry out the step? In this step we first find out that particular off-diagonal entry which has the largest absolute absolute value. Suppose that happens to be in row I and column J. And let that particular entry be P. Once you get that, you look at the 2 by 2 submatrix consisting of these things: the ijth entry, the jjth entry, the iith entry, and the jith entry. So these 4 entries, they constitute a 2 by 2 submatrix, and we are interested in only that. We apply our Gibbons transformation to only that particular submatrix. Everything else is remain unaffected. Now we have to understand this carefully. When we apply that matrix multiplication from the left, everything in this row and this row might change. I know that I am turning this into 0, so this will become 0, but as a result, these numbers in these rows will also change because I am pre-multiplying. So if I take any linear combination of these two, the same thing is applied to all the other entries in these 2 rows as well. However, every other row will be completely unaffected. Similarly, when we are post-multiplying, then all the entries in these 2 columns may change. However, the entries in the other columns will remain unaffected. Now let us see how this influences f of ak. So how f of ak changes to become f of ak plus 1. How does that change? Let's consider these 2 entries. When you apply the pre-multiplication, these numbers have possibly changed, but because you pre-multiplied by an orthogonal matrix, so the total sum of squares of these 2 entries must remain the same. They may be redistributed, but the total must remain the same. Since both of them are of diagonal entries, so both of them still remain within the scope of the f function. As a result, any change in these entries will not change f of ak. Same is true about these 2 entries, both being of diagonal. Same is true about these entries. The only exception will be these pair and these pair. Whenever you change these, you are moving part of the mass from the off diagonal to the diagonal. Since f keeps track of only off diagonal, as a result, f will go down. The same thing may be said about the columns. Any change in these 2 entries will leave the f function unaffected. So how does it change? These off diagonal entry p will become 0, and there the total sum of square will lose 1 copy of p squared. Similarly, this p will also become 0, and there we shall lose another p squared. So f ak plus 1 will be f of ak minus 2p squared. Now remember that p was the entry with the maximum absolute value among all the off diagonals in ak. As a result, by the argument that I have already mentioned, this must be less than or equal to twice n p squared. Remember, n is the total number of off-diagonal entries on this half, which is also equal to the total number of off-diagonal entries on that half. So twice n is the total number of off-diagonal entries. So you see, p squared must be greater than or equal to f a k by 2n. Now put the 2 things together and you can see how f a k plus 1 will be changing. That is equal to f a k minus this. So this will be less than or equal to f a k, the 2 and this 2 cancels, minus f a k by n. This was greater than equal to, but this became less than equal to because I have a minus sign here. And that is 1 by 1 minus n, 1 minus 1 by n, f of ak. This quantity is strictly less than 1, which shows that at every step f of ak plus 1 is basically coming down. What it says is that f of ak plus 1 must go to 0, and this factor being strictly less than 1, it will come down at a geometric pace and eventually approach 0, and that will complete the proof that all the off-diagonal entries must individually approach 0. There is just one final catch in Jacobi's algorithm. We know that for a diagonal matrix, the diagonal entries are the eigenvalues. Now, after the end of Jacobi's algorithm, when it converges, what you get is not a diagonal matrix, but a nearly diagonal matrix. They are not off-diagonal entries, but they are very small, say within some epsilon bound or something. Now, is there a result which says that if I give you a nearly diagonal matrix, then the eigenvalues are nearly equal to the diagonal entries? And this might look like a very stupid question to ask, but it is not that stupid, because the entries of a matrix will determine the coefficients of the characteristic polynomial, and the eigenvalues are the zeros of that characteristic polynomial. Now, it is a standard fact that the zeros of a polynomial depend discontinuously on the coefficients of the polynomial. That is, it is possible to tweak some of the coefficients a little bit, causing the zeros to change tremendously. Even the simple example of a quadratic polynomial will show that. If I look at the standard formula for the two roots of a quadratic polynomial, then we have a minus b plus minus square root of b square minus 4ac divided by twice a. Notice that in the denominator we have got twice a. As a result, the dependency of the zeros on the coefficient a is discontinuous. If you change a from minus 0.00001 to plus 0.00001, the roots might just switch tremendously from a very low negative value to a very high positive value. As a result, to say that we have nearly tweaked all the entries of a matrix slightly, or a matrix is very close to a diagonal matrix, does that immediately say that the eigenvalues must also be very close to the diagonals? No. This simple example of a quadratic polynomial makes us think twice. But fortunately, in case of a nearly diagonal matrix, we do have a result which says that the diagonal entries are indeed approximate eigenvalues. This follows from a rather less known theorem called the Gauss-Seidel theorem. That theorem is perfectly general. It does not work with diagonal matrix or real matrix or symmetric matrix. It is perfectly general. It works with any square matrix with possibly complex entries. Gauss-Seidel theorem is a theorem about any square matrix n by n over the complex field. In particular, it also applies for matrices which have got all real entries. Now, what it says is this, that you look at all the diagonal entries of A. So, these are of the form A, K, K. Now, it says that all the eigenvalues of A must lie within a certain distance of the diagonal entries. And they are done in the following way. So I consider a disk around each of the AK. So centered around AK, I consider all those complex numbers such that these are less than a certain quantity. This quantity will be the following. You look at all the entries in the same row as AKK except the diagonal, which is kth row, jth column, j not equal to k, all the off diagonal entries, and take absolute value of that. So you consider this set. So all complex numbers z such that this holds. So centered at AKK and with radius this, I am considering a disk. So if I give it a name, I will give it a name. Suppose I call it Tk for k from 1 to n. With this setup, Gauss-Corin's theorem says that all eigenvalues of A, they are all complex numbers in general, must lie in the union of all these decays. There cannot be any eigenvalue lying outside this thing. So if these quantities are pretty small, as they are going to be in our case after Jacobi's algorithm has converged, these off diagonals will be pretty small. So these things are something like less than epsilon or something, then the eigenvalues must lie very close to the diagonal entries. Now the proof of this fact is very simple. So suppose you take any eigenvalue of A. So let lambda be any eigenvalue of A. In that case, you surely can write that AV equal to lambda V for some eigenvector V. So this is also something with components coming from C, and this must be non-zero. That is part of the definition of eigenvector. If you allow zero vector, then naturally this will always hold trivially. Now what I do is that I look at all the entries of V. So V is of the form V1 to Vn. All these are complex numbers. I consider their absolute values, and suppose Vk has the maximum absolute value among all the components. So I assume for all I, Vk is greater than equal to Vi. Obviously there are finitely many things. So if I look at all the absolute values, one of them must be the maximum. The maximum may occur in multiple places also. I just take any one of them such that this will be greater than or equal to Vi. Now in this equation, both the sides are vectors. Consider the kth component of both the sides. So what do I have in the kth component? It is the kth row of A times V, that is A Kj Vj, j from 1 to n, and on this side I have lambda Vk. So I have Vk here, I have part of the Vk here also. I want all my Vks on one side. So what I will do is I will keep everything other than the kth term here, A, K, J, Vj, and bring that thing here, lambda Vk, and the coefficient of Vk will be here Akk. So lambda minus Akk Vk. Now I am going to take absolute value of both sides. So I will write this first. So lambda minus Akk times absolute value of Vk that is equal to absolute value of this by triangle inequality, that will be absolute value Akj times absolute value Vj, j not equal to k. Now I plan to divide by absolute value of Vk. Observe that since my V is non-zero, so this quantity must not be equal to 0. If even the maximum absolute value is 0, that means everyone else is 0, which means V vector will be 0, which is not allowed. So this is non-zero, I can safely divide. So I will have lambda minus akk less than or equal to summation akj Vj by Vk, j not equal to k. These quantities are always less than or equal to 1 because Vk was the maximum of them all. So this must be less than or equal to summation akj all modulus j not equal to k. And that is basically what I wanted to show, because this says that lambda belongs to dk. Now in this case, how did I choose k? I chose k based on that maximum component of the eigenvalue. So I do not know what k is given a particular lambda, but I know it must be one of those decays. That is why I have written union of all decays. It must land in one of the decays or other. So it must always be in the union. So that is the Gauss-Seidel theorem, and as I have already mentioned, the proof of the final fact regarding Jacobi's algorithm relies on that. Once you have converged to something which is nearly diagonal, you basically say that these things are pretty close to 0. Then the eigenvalues will be pretty close to the diagonal entries. In fact, most standard softwares will give the output of Jacobi's algorithm in terms of this radius. Instead of saying that the diagonal entry are the eigenvalues, they will say diagonal entry plus minus this quantity. So they will even give a precision measure. And since in our case we are working with real symmetric matrices, we know that they must be real numbers. All the eigenvalues must be real numbers. These are also real numbers. So it is something like this. This is my real axis and here is akk. So this theorem says it must lie within this particular disk. We know that since we are working with real symmetric matrices, it must actually lie only within this particular real interval. So that's how ideally the output of Jacobi's algorithm should be given.